everyone. Welcome to the Audio Precision webinar. Today we'll be discussing the fundamentals of audio test. Our General Manager, Daniel Knighton, will be leading the conversation today and will be providing demonstrations in APX 500 software. My name is Paige, and as the producer of the event, I would like to go over a couple housekeeping items before we get started. First, please note that this session is being recorded and it will be available to you after the webinar concludes. So you can expect to receive an email from me with a link to view the webinar if you wanted to rewatch it or share it with your colleagues. Secondly, we welcome questions during the webinar. So if you have a question for Dan as he's going through his PowerPoint or demonstrations, feel free to submit that via the chat function via Microsoft Teams. And we'll also pause at the end of the presentation to take questions at the end as well. So Dan has a lot of info to share with you today. So without further ado, Dan, I turn it over to you.
All right, thank you, Paige, and good morning, good evening, or good afternoon, as the case may be for all of you. Thank you for joining us. My goal with this session is really to introduce what I think are some of the most fundamental things you'll need to know if you're coming into audio test either completely cold with no prior background necessarily in test, or even if you are pretty familiar with test and measurement, but you haven't been making audio measurements before. So we'll talk about, in particular, what's special about audio test, what separates it from other signals you may have been measuring or familiar with measuring. We'll go through the most common units of measurements. We'll talk about different kinds of test signals we use and why. And then we'll go through some of the most fundamental measurements that we'll make really when testing any audio device. It's a bit to cram in, so we'll be going at a good clip. Feel free to submit those questions via chat, and we'll pause throughout the presentation at various times to try and address those questions as they come up. So let's start by talking about what's special about audio test. One of the things that I see quite a bit is, generally speaking, we're talking about measuring an AC signal with a bandwidth less than 20 kilohertz. And well, why can't we just make that measurement with, say, a handheld multimeter or an oscilloscope or some other kind of off-the-shelf, or I'll say common instrument? And well, the direct answer is you can. A multimeter will measure an AC voltage. A scope works just as well, but there are some unique characteristics about audio signals that lead us to want to use some specialized equipment. The first of those is the extremely wide range of amplitudes we'll measure in audio signals. So on the electrical scope, a state-of-the-art digital to analog converter will have a self noise measured in microvolts. At the other end of the spectrum, the kind of power amplifier that will drive the speakers for a stadium rock concert might be outputting 200 volts RMS. It might even be above 200 volts RMS. So compared to the range of voltages that a handheld multimeter might address, we're often talking about a range of 180 or even 200 dB from the smallest signal to the largest signal that we want to measure. In terms of just human hearing, the threshold of hearing is generally thought to be around 0 dBSPL, and humans can withstand 120 dBSPL or even as much as 140 dBSPL. Of course, there'll be some hearing loss at that upper range, but really even just within the range of human hearing, we're talking about a range of more than 1,000,000 to 1. So it's really this very, very large amplitude range, and we can't statically compensate for it. You know, on an oscilloscope, you might change from a 10x probe to a 1x probe, but here we're talking about a continuous AC signal, and that dynamic range could change, you know, instantaneously. The other thing to think about is perhaps not the bandwidth of the signal, but the frequency span of the signal, for example, in octaves. Range of human hearing is generally accepted to be from about 20 hertz to 20 kilohertz. That's 10 octaves of frequency range. It would be a bit like imagining a radio that could tune from the AM band all the way to microwave signals. If you think about typical RF spectrum analyzers, they're not designed to address that kind of range of frequencies. You know, if you think about radios, you know, radios, we typically think of tuning them within an octave range, within a fraction of an octave range. So the idea of addressing 10 octaves is quite challenging. And then when we get to actual measurements, well, as a practical matter, we typically want to look at everything from DC, so offset voltages in converters and power amplifiers, all the way up, essentially. If we're testing a Class D or a switching power amplifier, we might want to see everything from the DC offset of that device to the out-of-band components of its noise shaping system. So that practically gives us a limit that's as far up as you can imagine, but typically we see from DC into the low megahertz. And as we meet those requirements of amplitude range and frequency range, we have a very high concern with spectral purity, or the residual noise and distortion in the signal. Again, human hearing is pretty amazing. Humans can discern distortion products that are well below the ambient noise floor. And today, pretty high quality, but not esoteric consumer devices are available that have 100 dB of dynamic range. So this is, you know, the three things together is really what drives us to specialization in the type of equipment we use for audio measurement. Now, in terms of units, to be frank, there is a world of units that are used in audio measurements. Going back to the title of this seminar, we're going to talk about the most fundamental ones. And frankly, depending on your exact measurement domain, the unit might be pascals or volts. I might argue, given my own background, is that it's really volts, and I'll explain that in a moment. But the first thing I want to talk about is that when you see the notation V by itself, just volts, that's ambiguous, because as soon as we're talking about audio, we're talking about an AC signal, and we need to disambiguate. Do we mean the peak value of that AC signal? Do we mean the RMS value of that AC signal? Are we measuring a DC signal instead? That does come up quite a bit. So It's not necessarily always called out, and it's kind of annoying when it's not called out, but ideally the type of volts, if you will, is always explicit. And let me give you a little idea of that. So let's just jump into our software. And this is a digital loopback right now, so it's very perfect. But we'll just set this to generate 1 volt RMS. And if we look at our oscilloscope view, we have a nice sine wave. And what you'll notice immediately is the peak value of this is actually going to be 1.41 volts. And I'll explain where that comes from in a second. But one thing to be clear is the peak value of this signal is 1.414 volts. The peak to peak value, which is from the maximum positive extent to the maximum negative extent, is of course just twice that amount. The RMS is, if you will, the area under the curve, okay? Or another term that's a little bit obscure but explains what's going on is the heating power into a given resistance. That is to say, if you drove this signal into a given resistive load, how much would that load heat up? And that's described by the RMS energy of the signal. But volts is, I'll say, at the root for test instrumentation. Now, there is no human being who listens to volts. So arguably, the more native unit for audio signals is pascals. It's a unit of sound pressure. So it is a direct analog to volts. Volts is in the electrical domain. Pascals is in units of sound pressure. It's what our ears actually detect. And sound pressure is newtons per meter square. 1 Pascal equals 1 Newton per meter square. Now, to give you some perspective on sound pressure, if you listen to an audio signal at 1 Pascal, that's loud. You can try it for yourselves if you want. Some of you probably had. It's loud. It's not unsafe. It's not uncomfortable. Many people voluntarily listen to music at that sort of sound pressure level, but it's definitely loud. But in fact, what's happening is sound is a small AC signal riding on top of a very, very high DC offset, which is the static atmospheric pressure. At sea level, roundabout, there's about 100,000 pascals of atmospheric pressure. And you can then work out that a pretty high AC signal in terms of sound is going to be really a small signal riding on top of that static pressure. Now, the reason that I might argue that volts is more fundamental, and that really gives way to my bias in the audio measurement industry, is that there is no analyzer that natively measures volts. Instead, we always using some type of transducer, a device that converts from one domain to another. We call it a microphone, but the input to the microphone is sound pressure level, and the output is electrical signal. And in our analyzers, in some location, there is a place for us to enter the ratio, or we commonly call it the sensitivity of our transducer, which will tell us the conversion from pascals of sound pressure to volts, so we can then express it in our software and look at measurements in the domain of pascals. But really, the analyzer itself is measuring volts. Now, the next family of units that I want to talk about a little bit deviates a bit, and it's perhaps the most synthetic unit, and that is when we are representing digital audio. So we're no longer talking about a continuous analog signal. We're talking about a digital representation of the audio. In this context, you'll see the base unit is typically called FS for full scale, and I'll talk about a related unit that Audio Precision uses called D. The thing that is difficult or confusing about FS is that there are a variety of different representations of it, depending on, frankly, the industry or the domain you're in. And unlike volts or pascals, which are defined by an international standard, they're defined as SI units. FS is just an understanding, if you will. Everybody assumes certain things about it. The most common definition, and the definition that Audio Precision uses, comes out of an Audio Engineering Society standard, number 17. And it is exactly as it says. FS is the RMS amplitude of a sine wave whose peak reaches the maximum digital code in a pulse code modulation sampling system. So let me just show you what I mean by that. So I'm going to generate a full scale signal, a signal that has an amplitude of 1 fs. And this signal that has an amplitude of 1 fs, if I look at its time domain representation, you can see that it reaches this maximum digital code of +1 and -1. Now, here's the part where FS can be a little confusing. If we were talking about volts and we said, oh, I have a signal, a sine wave, and it has a RMS value of 1 volt, the peaks of that sine wave would actually be reaching a greater value. And I'll explain that in a moment, but I'll give you a hint. It's related to the crest factor of sine wave. FS is not volts. There is not a commonly understood instantaneous value for FS. FS is intrinsically defined as an RMS, root mean square, or average value of a signal. What Audio Precision has decided to do is when we describe the instantaneous value of a digital signal, we use a different unit, D. So where with volts, we have a subtext which tells us whether it's an instantaneous or RMS value. With FS, FS means RMS, and in the context of an audio precision analyzer, D means instantaneous digital level. So as I was showing you on that screen, a digital sine wave with an RMS value of 1 FS will have a peak value of 1 D in audio precision APX analyzers. Now, this is a very quick glance at units. And what I will say is that there are many, many units beyond volts, pascals, and FS. But these are likely the most fundamental units. They're the units that all the most basic audio measurements are going to be made in. Now, one thing that we should pause and talk about for a moment before moving beyond units is dB. dB is used all the time in audio measurements. Most audio measurement units are expressed in dB. And dB stands for decibels. And there was a gentleman named Bell, and that's why the B is capitalized. So a dB is a tenth of a bell. dB by themselves is just a logarithmic ratio. That is to say, if you say 20 dB, that is exactly the same as saying 10 times, okay? And because of that, anytime a result is expressed, dB needs to be related to what the ratiometric reference is. That is to say, if somebody were to say, oh, my result is 90 dB, by itself, that would be as if they said, oh, my result is 42%. Well, 42% of what? So some very common dB units that you'll see, especially in audio, dB volts or dBV. So this is dB relative to 1 volt RMS. So 0 dBV is 1 volt RMS. dBu, and I'll talk about the relationship between dBu and dBm in a moment, but dBu is just dB, but instead of relative to 1 volt RMS, it's relative to 0.7745 volts RMS. And that sounds a little funny. Where does that come from? Well, where it comes from is a long time ago when most electrical audio interfaces were based on 600 ohm termination. Instead of expressing things merely as volts, they were expressed in terms of power dissipated into 600 ohms. And that unit was dBm. dBm was originally relative to 1 milliwatt dissipated into a 600 ohm load. Now, one little diversion, if you're talking about dB power, that's a different logarithmic ratio than dB energy, and that's because of the extra squaring function you have in power measurements. Now, in most audio measurements, when people talk about dBm, it's really being misused because 600 ohm terminated analog interconnects are quite rare. So dBu was invented to represent the voltage that a dBm system would have into an open circuit. dBSPL is another common unit, perhaps the most common unit when we're talking about sound. So this is dB relative to 20 micropascals. So 0 dBSPL is commonly understood to be the threshold of human hearing. Now that's arguable if it's exactly right, but it's pretty close. So you can think of this as dB relative to what a human could hear. 94 dBSPL is 1 Pascal, give or take a little bit. I'll show you that in a moment. And then dBFS is dB relative to digital full scale. So 0 dBFS is the maximum RMS signal that a sine wave can represent in a digital sampling system. Now, a couple or a few handy ratios to keep in mind when talking about dBs, so you can do some quick math in your mind, is plus minus 6 dB is double or half. So 6 dBV is 2 volts RMS. Now, this is a logarithmic ratio, so to be really precise, it's 6.02 dB is doubling or half. 10 dB is approximately a third. And 20 dB is 10 times. So 1% is minus 40 dB. This might be a good moment to take a pause and see if there's any questions so far. Paige?
Yeah, thank you, Dan. I've got some feedback that this is very useful, and someone wants to confirm that a plus 3 dB is a level of twice the energy, plus 6 dB for twice the voltage as explained.
Sorry, plus 6 dB is twice the energy, plus 3 dB is twice the power. So I haven't spent too much time talking about the distinction between power and energy in dB, because most of the measurements we make in audio are energy measurements, but just to correct that, plus 6 dB is twice the energy, plus 3 dB is twice the power.
Great, thank you, Dan. And one more question, just on, it looks like some semantics. Some people are indicating that they're used to seeing a lowercase d and then a capital BU referenced as lowercase b, uppercase BU. Is there a difference for that, and what's the standard?
Sure. There is no difference. Lowercase d, uppercase B, uppercase U is the same as lowercase d, uppercase B, lowercase u. I have to admit that I cannot stand on any particular authority, and I'd have to look it up in SI, but my understanding is the correct way to print it is lowercase d, uppercase B, lowercase u, but I'll have to admit that I could be wrong. But in either case, dBu is dBu. There's not a difference in the unit based on exactly how you, what case you put the letters in.
Great, thanks, Dan. And one more question, is there any unit as dBA or lowercase d, uppercase B, lowercase a?
Sure, and I'll talk about that in a moment, but the simple answer is unfortunately a little bit confusing, but the most common understanding when you see dBA is it is dB SPL, so dB sound pressure level, so dB relative to 20 micropascals, that has had an A weighting filter applied to it. And this is a very common unit you'll see in reference to room acoustics or room noise. If somebody will say, oh, the sound level in this room is 52 dBA. And if they wrote it all out, they should say 52 dBSPL A weighted, but that is very, very often contracted to dBA. And that's generally one thing I'll say that can be a problem with audio units, is that there are a lot of informal contractions in the world, and they create ambiguity. I mean, I'll say the most common one is where people say, oh, this is X volts. If you don't say whether it's volts RMS or volts peak or volts peak to peak, it is left to the interpretation of the reader to try and figure out what you mean from context. And dBA is very widely understood in the acoustics world, so I think a lot of people take it for granted, but it has the same sort of ambiguity. Okay, moving on, I want to just touch on this question of crest factor. So crest factor is pretty straightforward. Crest factor is the ratio between the peak level of a signal and the RMS level of a signal. And one thing that you will see over and over and over again come up is 3 dB. And it comes up because the crest factor of a sine wave is 3 dB or 1.414 or the square root of 2. And we may all be familiar with this from geometry class. A square wave has a crest factor of 1 or 0 dB. And one thing that you will see is that I'll call them real world test signals. So noise, human speech, typically has a much higher crest factor. Crest factors of 5, 7, 10, 20. And what that means is that the peak level of a signal relative to its RMS level, or if you'll go back, the amount it could heat a resistor of a given value, goes up and up and up from a sine wave. And the reason I really want to raise this is there's something that can generate some confusion with audio precision analyzers, and that is that when you set the signal generator, if you're generating something other than a sine wave and you set the signal generator in RMS, that can fake you out because the RMS level of the AP signal generator is actually assuming that that is a sine wave. And this is very confusing. Unfortunately, there is a reason for it, which is if you're generating a sine wave and you change the waveform type to another waveform, you'll have the same peak value as that sine wave, and that guarantees that you won't drive your device into clipping. Okay, let's talk about some test signals. There are a lot of test signals in the world, but the one that is by far the most common test signal to use in audio measurement is the sine wave. And we can talk about all the issues with sine waves, but the very brief overview is this. A sine wave is the only signal that has all of its energy at one frequency. So that means that when we drive a sine wave into a device under test, and we look at the output of that device under test, everything, all the energy that's not at the frequency of our stimulus is something else, something usually undesirable, noise, distortion, other products. So in that sense, a sine wave is like a test probe. It's a way for us to probe our device under test and exactly characterize its behavior. Another test signal that's very common, especially in acoustic measurements today, is a continuous sweep or a log chirp, or sometimes you'll hear people call it a farina sweep. This is a sine wave, but it's a sine wave whose frequency varies continuously with time. And I'll play samples of all of these in a moment. Pluses, it allows a very, very fast characterization of a device under test. You can extract the frequency response and distortion of a device in just, potentially less than a second. One disadvantage is the mathematical technique that's involved does not give you a noise result. So you get the distortion of a device, you do not get its distortion and noise. A third test signal is a multitone. A multitone is, again, a sine wave, but imagine a sine wave made up of all the test frequencies you wanted to check simultaneously. So this, again, is a technique where we can get very fast frequency response, distortion, and unlike the log chirp, we can also get noise. The disadvantage is the distortion we'll look at is not just harmonic distortion. It also includes intermodulation distortion, and that makes comparisons to a classic single tone THD measurement difficult to make. And also because we're playing multiple sine waves simultaneously, the energy in each sine wave is lower than if we were playing just one. Now, particularly in acoustics, noise itself is a very common test signal. And we don't just use any noise. I'd say the two most common is white noise, where we're looking at a signal which has a statistical distribution that gives us an equal amount of energy per frequency, or pink noise, which is an equal amount of energy per octave, which results in there being less energy as frequency goes up. I'll show, and we'll listen to each of those. One thing to keep in mind is pink noise to many people sounds more natural. If you just look at the spectrum of noise in, I'll say, the natural world, it has a very pink characteristic. There's more low frequency energy than high frequency energy in the world, acoustically. Now, finally, speech and music. One of the issues with all the preceding test signals we've talked about is, in some sense, they're unnatural, in the sense that no one listens to sine waves for pleasure. Nobody listens to noise for pleasure. So as a practical matter, one issue is that a lot of systems today include complex signal processing in order to try and filter out things like background noise, and those systems might filter out our test signals. So in those cases, there are measurement techniques, FFT transfer function, that allow us to make measurements of a device using an arbitrary signal, and more specifically letting us use something like speech or music as our test signal. So talking about some fundamental measurements, the most fundamental measurement is just measuring the amplitude of an audio signal. Now, even this measurement has some peculiarities we want to understand. And the biggest I want to touch on is what are we measuring? Typically, if you would look at something like a multimeter, when you set a multimeter to measure AC level, it just provides a readout. In APX, the equivalent to that is our level and gain measurement. And we describe this as a broadband measurement. So it measures all the energy in the currently defined instrument passband. So it measures both your fundamental, any noise, any distortion, all of that gets added together, and you just get one result. If that's what we want, that's great. But sometimes we're looking for peculiar things. So audio precision also provides another level measurement, which is a noise measurement. Now, this is, again, measuring the RMS level of all the energy in a certain bandwidth, but relative to the question about what does dBA mean, sometimes when we measure noise, we want to apply a weighting filter, such as an A weighting filter is very common. So in that case, we want to apply some filters to our noise measurement. And in addition, by its definition, noise is a random thing. When we're measuring noise, it becomes critical to understand, well, what's the integration time? Because if we sample our noise for, say, 200 milliseconds, we'll get a value, but then the next time we sample it, we may get a different value. So we may want to sample it or integrate the measurement over a longer period of time. And then maybe we don't want to measure all the energy in the passband of the analyzer. Maybe we want to measure only the energy at a specific frequency point or over a specific frequency span. So we have a band pass level measurement. So this is, again, a measurement of the signal amplitude, but over a controlled and specified bandwidth. So one thing that will be critical in these measurements is, what is the passband? What is the range of frequencies over which we're making our measurement? And then, are we applying a weighting filter? And let me talk about that for a moment. So human hearing does not have a flat frequency response. Humans have biases in the way we hear sounds that lead us to emphasize and de-emphasize sounds. And that function is complex. It varies with frequency, it varies with amplitude, and it even varies with time. But over history, we've developed various approximations of that hearing response, and that results in weighting filters that attempt to weight a signal according to human perception of that signal. A weighting is probably by far the most common, but there are a lot of these filters. Even in this graph on the screen, I'm only showing you a selection of the available filters. And this is something that's going to come out of any test specification you might be looking at. So just to take a practical look at what this means. So here we have, I actually have a speaker and a microphone in the room with me. We're looking at the sound level in this room as I talk, just in dBSPL. And what we have is a level measurement right now, because I'm not generating a signal, just of the ambient noise. If I turn on my signal generator, you can see I now get, in our FFT spectrum monitor, I can see the fundamental at 1 kilohertz, and we can see how much sound pressure that generates. Now, one thing to realize is right now, this includes not just the level of the test signal, but also the level of all the ambient noise. And if I turn this down enough, you'll notice that if I look at my FFT spectrum monitor and I stop talking for a moment, you can clearly see the fundamental is present, but in this level measurement, which has no bandwidth constraints, it is being swamped by the ambient noise. Now, if I go to my bandpass measurement, and I'll generate the same small signal, but here what I've done is I've set my analyzer selectivity to window width, which is the most selective I can make it, and I'm tuning that to the generator frequency. Now I can make a measurement just of the 1 kilohertz tone, because I've set the analyzer to exclude all the other energy from that measurement. And then let's look at this a different way. So here is a noise measurement. So I'm not generating any signal on purpose. Let's say I wanted to measure the ambient noise in the room. So a few things to be aware of. Here in our noise measurement, we have a high pass filter and a low pass filter. And so this is right now set to measure the noise within the range of human hearing. And this is exactly where I might say, oh, I would like to apply an A weighting filter to this. So this is now telling me the noise level in this room in dBSPL A weighted. Now you'll notice that this measurement is varying quite a bit, and that's of course partly because I'm talking, but also partly the random nature of noise. So this is a case where I might go into advanced settings, acquisition time, and set my acquisition time at, say, 5 seconds. And that will stabilize the measurement or make it more repeatable by integrating it over a longer period of time. Okay, I'll take a little pause there to see if we have any questions at this moment.
Hey, Dan, yeah, I've got one question in the queue about Fletcher-Munson curves, or can we measure audio in general against a Fletcher-Munson curve?
That's an excellent question. So I glossed over that. The Fletcher-Munson curves, for those who are not familiar, are the product of a set of studies that were done a long time ago on human hearing, and they're fully properly called the equal loudness curves. So these are studies done with human listeners where sounds at different frequencies and different levels were played for the listeners, and they scored those sounds according to how perceptually loud they sounded. And the A weighting, B weighting, C weighting curves are essentially inverse Fletcher-Munchausen curves. And in fact, they correspond to different sound pressure levels. One thing that's often overlooked is the A weighting curve is meant to apply to a certain ambient sound pressure level. I've glossed over that a little bit. It's a little bit of a more advanced topic, but that's just a quick overview of them, and I highly encourage anybody who's curious to do a little Google action on them. But they are the product of research that tells us at a given frequency, how loud does something have to be in sound pressure level to sound as loud as a tone at a different frequency. Okay, just to use the most of our remaining time, phase, group delay, and polarity. So this often just gets lumped under phase, which is really the time alignment between two or more signals. But there are a few subtleties. So the first is a lot of the time, if we're testing, say, a stereo music playback device, what we're interested in verifying is that the two channels are perfectly in sync. For example, sometimes you'll get into a situation where there's a little DSP coding error, and one of the channels is delayed relative to the other channel by one sample. And that is very apparent to a human listener. So that would be interchannel phase. And if you were looking at that kind of signal on an oscilloscope, for example, that's what you'd see in our top image. Absolute or input to output phase is the delay expressed in degrees between the signal at the input of a system to the signal at the output of the system. And any filter, which is what a loudspeaker ultimately is going to have some input to output delay. And so that can be expressed as absolute phase or input to output phase. And this is a big property of any kind of filter that you'll look at. Now, closely related to input to output phase is group delay. Really, these are not reciprocals of each other, but they're convertible from each other. So group delay is the delay in time as a function of frequency of a device. And if we look at the lower graph there, we're looking at the group delay of a speaker, and one of the things you'll notice is it has significant delay at low frequency, and that's a property of that device. The final thing I'll touch on vis-a-vis phase is polarity. So we're talking about an AC signal when we talk about audio, and the question is, if you inject a positive going waveform into the device, does a positive going waveform come out of the device? And in the case of, for example, a speaker, you can just reverse the voltage terminals. Now, polarity is not normally important unless you accidentally reverse it. So for example, if you have a headphone and the polarity is reversed on one of the ears, that will sound terrible to a human listener. Now, the thing about polarity is actually most audio measurements don't reveal polarity, right? A signal with reverse polarity is going to have the same RMS level. A couple ways you can look at polarity is one is what we call a polarity waveform, which is an asymmetric AC waveform. And the other is to look at the impulse response of a device. Both of those will tell you the polarity. Now, I'm sorry that I saved this almost for last because it's really one of the most fundamental measurements today in audio, but let's spend our remaining minutes on FFT spectrum analysis. I am not going to, obviously, in a few minutes, dive into the whole world of the Fourier transform. I just want to cover what you need to know, which is that the Fourier transform is magic. It takes a time domain signal, such as a sine wave, and represents the energy in that signal as a function of frequency. And this can be incredibly useful because out of this representation can come all the measurements we want to look at. So we can get distortion, we can get noise, we can find the amplitude of our signal. All of these things can come from looking at the spectrum of the signal. And this is actually how most, but not all, audio measurements are made today, is by digitally sampling a signal, doing a Fourier transform of that signal, and then divvying up the energy by frequency and sometimes summing and sometimes dividing to arrive at all the different measurements we want to see. Key things to understand about FFT analysis. So it is done on a discretely sampled system. So we take our continuous waveform, we pass it through an analog to digital converter, and we analyze the values of those discrete audio samples. The frequency resolution in hertz is equal to the sample rate divided by the acquisition length. The acquisition length is the number of samples we recorded. So if we had a sample rate of 48 kilohertz and we acquire 48,000 samples to do our FFT analysis on, we will have a frequency resolution of 1 hertz. And the frequency resolution is important just because we won't be able to suss out features that are in the same FFT bin. So let's say our frequency resolution is so low that two signals that we're interested in just show up in the same bin. We won't be able to suss them out. There are, I'll say, two common ways in which we might scale FFT graphs. If we're looking at sine waves or any repeating signal, and we want to know the amplitude or level of that signal, we'll use RMS scaling. But if we're looking at noise, we want to use what's called amplitude spectral density. Now, these are just different ways of scaling the math, and they're both the same when the frequency resolution is 1 hertz. Unfortunately, I see that we have used up our time in this 1-hour session. What I'd like to do now is entertain any remaining questions I can address this morning.
Great, thank you, Dan. So I do have a couple questions here in the chat. The first question is, what exactly is A weighting?
So A weighting is this. Well, let me just show you in the software. So A weighting is a weighting function where we attenuate the signal at low frequencies and high frequencies and actually gain it a little bit in mid-band frequencies to represent the sensitivity of human hearing at different frequencies. So for example, in this room, if I say no waiting, we have a apparent ambient noise level of 67, 68 dBSPL. If I A-weight it, I'm trying to approximate how loud that would sound to a person. And you can see it's a little bit lower. It's a little bit, if you will, the way outside when we measure temperature, we measure the temperature, and then some weather reports will provide the wind chill factor, which is how cold that would actually feel to a person. So this is a similar concept, and A-weighting is one of a variety of different weighting filters that have been developed over time to approximate that.
All right, thank you, Daniel. So I've got another question. Does multi-tone give response closer to what music is?
That is a deep question. I will say I will make the following statement, which we can follow up on, but it's really almost its own topic. An audio device that is linear and time invariant. So what I mean by that is an audio device where the output of a system has a linear relationship to the input of a system and whose behavior doesn't vary over time will have exactly the same measurements regardless of the stimulus signal that's used. It could be multi-tone, it could be sine wave, it could be speech or music. However, real world audio devices have various nonlinear and time variant effects. And particularly when we talk about speakers, speakers heat up as you play a signal through them and their behavior changes. And one observation is the crest factor of a sine wave, of a pure sine wave, is so much lower than that of typical music that it will heat up a speaker much more. So there are a number of papers that have been published about the subject of measuring things like speakers with signals that more closely approximate the crest factor of music in order to see a more representational response from the device under test. I realize that's a very shallow answer, but the answer is really, it depends. There's certainly a valid argument to be made that a multi-tone can more closely approximate the energy distribution of music and is therefore perhaps a more appropriate test signal in some cases.
All right, thank you, Daniel. Another question from the chat here. How do you choose the filter and filter size of an audio analyzer?
So that's one of those questions where the answer is going to come from the test specification of the device that's being measured. And that will have to do with, the marketing department will be involved, the product designers will be involved, but it's not a question whose answer, lives in the abstract. It's, well, we're making a power amplifier and it's designed to be sold into the consumer market for home listening, and so it needs to have so many watts of power, and we're going to specify its noise a certain way. So unfortunately, there's no cut and dried answer to that, and it's not perfectly deterministic. It is a product of however you've come up with the specifications for your device under test.
Great, thank you. And Dan, I've got another question that may be slightly out of scope, and you can tell me if you'd rather me follow up with this person after the event. But I do have a question on FFT. And the question is, will FFT of a flat signal appear flat?
That is a very complicated question, actually. So it depends, and I think we'll best to take it offline. I will say this: if you stimulate a device that is perfectly linear and time invariant, a cable, for example, with white noise, the FFT of that will be a straight line. But it depends on your test signal, if you know how you deviate from that and what the behavior of the device is.
Okay, thanks for that, Dan. And another question: what does coherence mean?
That's another good advanced question, but very simply, if we stimulate a device with a signal, the degree to which the output signal matches the input signal in amplitude and phase across frequency is the coherence. So a device with a coherence of 1 or 100% is a device where the output signal matches the input signal at all frequencies in both magnitude and phase.
Thanks, Dan. I've got one final question here, and again, this one might be slightly out of scope for this event, but I do have a question. Is there a way to measure a peak level or look at the signal in the time domain, as an example, to test a signal processor with a peak limiter?
Yes. So yes, how you actually do it is a little bit more complicated, but we do in fact have a tech note on our website that describes testing compressors and limiters with APX.
Awesome. Thank you, Dan. That's all the questions for now. And ladies and gentlemen, if you have any other questions or would like to discuss your application in more detail, feel free to reach out to our tech support team at techsupport@ap.com. And I'll also include that in a follow-up email so you can reach out to them directly. They're a great group that can help support you. So that said, Dan, I think we are ready to conclude this webinar.
All right, well, thank you everybody for your time. I believe we'll have some follow-ups to this webinar, some additional webinars where we'll keep going and cover the rest of these topics.
Great. Thank you, Dan. Great work. And thank you everyone for attending. Please look for additional webinars coming from us in the future as well that cover more in-depth topics. Have a great day. Take care.